Hi, my name is George Tong, and this is my presentation of Lab 5, Faraday's Law. The purpose of this lab was to collect time data for a falling bar magnet through a tube of aluminum foil to help better understand and visualize Faraday's Law. And the fundamental concepts we need to know for this lab are the Biot-Savart Law, Faraday's Law, and Newton's second and third laws. A brief overview of the results we got. For the experimental average time, we got 1.246 seconds. And from the computational model, we got 1.124 seconds. Here are the measurements for the lab. The length of the tube was 0.3 meters. The width of the tube was 0.006 meters. The inner radius of the tube was 0.02 meters. And the whole radius of the tube was 0.032 meters. 3.245 was my mu from lab 3, which is what I used for my first computational model. And the mass of the magnet was measured to be 0.025 kilograms. And running 5 trials of the experiment, I got an average time of 1.246 seconds. Now I'm going to get into some snippets from my GlowScript code. So this first part and the second part is just me taking those measurement values from the previous slide and translating them into Python language. And here we have the code snippet for the calculation of the magnetic field. This is the code to calculate the magnetic flux. And to calculate the net force would be the summation of the gravitational force and the magnetic force, and achieve that with these snippets of code. And this is the snippet of the actual model running. It's an arbitrary time value, but the red indicates the north pole of the magnet, while the blue indicates the south pole of the magnet. The velocity versus time graph on the left was using my calculated mu from lab 3, which was 3.245. And that didn't produce a time result that was close enough to the experimental time result. So I adjusted the mu value and ended up settling on mu equals 4.9, which got me a time result that was close enough of 1.124. And the graphs look different as a result of it. So finally, post-lab questions. What if the resistivity of the conductor was reduced as close as possible to 0? Well, according to Ohm's law, because resistance is in the denominator, that would maximize the induced current. And because the whole reason why the magnet slows down in the first place is because it's a motional EMF type situation, the current is responsible for slowing down the magnet. So you can only imagine that a stronger magnitude of induced current would result into a stronger factor of slowing down. So what if holes or slots were cut into the tube? Well, it depends on how the holes are cut, because if it's cut in a drastic way, it would reduce the number of rings that would be available, which would decrease the magnetic force, and therefore the magnet would fall quicker. But if it was just a tiny hole, I think it would have a negligible difference.